Now here we are discussing about the groups. A group G is a set of elements with an associated binary operations, and we will represent this by comma and dot. It is sometimes denoted by, this is the sign of set in middle bracket, G comma dot. For each ordered pair AB of elements in G, there is an associated element A dot B such that the following axioms holds. Like for the closure, if A and B belongs to G, then A dot B belongs to G. Same associative property, A dot and B dot C equals A dot B dot C for all A, B, C belongs to G. Identity element, there is an element E belongs to G such that A dot E equals E dot A equals A for all A belongs to G. And for inverse element, for each A belongs to G, there is an element A dashed belongs to G such that A dot A dashed equals A dashed dot A equals E. A finite group is a group with a finite number of elements. Otherwise, a group is an infinite group. A group is said to be an abelian group if it satisfies the following condition. Commutative, A dot B equals B dot A for all A, B belongs to group. Example of abelian groups: the set of integers negative, 0 and positive Z under addition. The identity element of Z under addition is 0. The inverse of A is minus A for all A in Z. The set of non-zero real numbers are and this symbol under multiplication, the identity element of R star under multiplication is 1. The inverse of A is 1 by A for all A in R. This is the multiplicative inverse, and this is the additive inverse. And for the exponential and cyclic groups, exponentiation with group within a group is a repeated application of the group operator such that A to the power 0 equals E. The identity element A to the power n equals A dot A dot A dot 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 up to A, that is applied dot applied n minus 1 times, because here for 2A there is single dot, for 3A there will be 2 dots, so for n A there will be n minus 1 dots. A to the power minus n equals A dashed n, where A dashed is the inverse of A. Here A dashed is equal to 1 by A, inverse of A to the power minus 1. So here A to the power minus 1 into n, so A to the power minus n. So we can write A to the power minus n in the form A dashed n. A group G is cyclic if every element of G is a power G to the power k. K is an integer of a fixed element G, small g belongs to group. Here G belongs to G. G is the subset of G. The element G is said to generate the group or to be a generator of the group. A cyclic group is always abelian and maybe finite or infinite. Example of cyclic group: here you can see the example, the group of positive integers n and plus. Here n is for the natural numbers, and here the sign n equals 1 2 3 dot to dot under addition is an infinite cyclic group generated by the element 1, that is 1 plus 1 equals 2, 1 plus 1 plus 1 equals 3, and etc. For the rings, a ring R denoted by R plus and this cross sign is a set of elements with two binary operations called addition, plus, and multiplication cross, such that for A, B, C in the ring R, addition and multiplication are abstract operations here. Like R is an abelian group with respect to addition For this case of additive group, we denote the identity element as 0 and the inverse of A is as minus A. Closure under multiplication, if A and B belongs to R, then A cross B is also in R. Associative or multiplication, A cross B cross C equals A cross B cross C for all A, B, C in R. Distributive laws, A cross B plus C equals A cross B plus A cross C for all A, B, C in R. A plus B cross C equals A cross C plus B cross C for all A, B, C in R. Here one thing should be noted, that A cross B as simply AB, because both are in product form, so we can write A cross B in terms of AB also. Like for commutative rings,